Hi, everybody. Today we're going to do the section 2.6. Well, this video is, I should say, is on 2.6. And 2.6 is the second derivative. Now, what is the second derivative? That's very simple. You just take a derivative, and then you take the derivative of the derivative. That's your second derivative. Very simple. And another important concept is concavity and the relationship between second derivatives and concavity. So let me just first of all give you an example of a second derivative. So let me switch the camera. I'm going to switch the. Let's see. I have to get rid of the share screen. I have to switch the camera, and let's try that again. Switch the camera. Yeah, why is it? Something is odd. So if we have y is equal to x to the 7th plus 5x to the 4th minus x to the negative 5th, then y prime is going to equal 7x to the 6th plus 20x to the 3rd plus 5x to the negative 6. And this is what we call, this is just, we're going to call this, we've been calling this the derivative. Now we're just going to refer to it as the first derivative. The second derivative, we write it this way, y prime prime, or y double prime, whatever way you want to say it. The second derivative is just the derivative. I'm just going to take the derivative of y prime. So that's all I'm going to do. And let's get this. Y double prime is now going to equal 42 x to the 5th plus 60 x squared minus 30 x to the negative 7. How did I get these numbers? 6 times 7 is 42, and the 6 rolls down to a 5. 3 times 20 is 60, and the 3 goes down to a 2. Negative 6 times positive 5 is negative 30, and the negative 6 goes down to a negative 7. So this now is the second derivative. And if I would take a derivative, now that's all we're doing in 2.6, but just to give you the idea, going forward, if I would take the derivative of this last guy, so I write y triple prime, so that's 5 times 42 is 210, x to the 4th, plus 2 times 60 is 120 x, plus 210 x to the negative 8, because negative 7 times negative 30 is 210. And this would be the third derivative. So just very, very simple. It's very, very simple. What we mean when we say a second derivative, it's no magical thing. It's just taking the derivative of the derivative. And that's the, and I could take second, third, fourth, fifth, sixth. I could, there's no, you take as many derivatives that you could keep going as long as you want. Sometimes the derivatives will keep on going. Sometimes they'll sort of stop. Meaning to say that sometimes, for example, if you have, let me give you an example here. If you have y equals x squared, then y prime equals 2x, y double prime equals 2, y triple prime equals 0. And if I continue, if I take, this is how you usually write it. You write the fourth derivative, you write a 4, but inside parentheses. Well, that's also just 0. And then it's going to keep on going, 0, 0, 0 down forever, because the derivative of 0 is 0, and so on and so forth. X squared to 2x to 2 to 0, 0, 0. It's just going to keep on staying zeros forever. On the other hand, if I have y equals e to the x, y prime equals e to the x, and y double prime equals e to the x, and y triple prime equals e to the x, and so on and so forth. So I could keep, so it's not just going to hit all zeros, it's going to just keep on, and so on and so forth. So, but you could take derivatives, in theory, you could take derivatives as long as you want. Even though it might start to get very monotonous, but sometimes not always. Anyway, back to the case at hand. Now, I want to discuss the other concept, this concept of concavity, and let's just the textbook actually has a very nice rendition of this. Let's just look at the textbook now. I'm going to switch cameras. Okay, and let's share my screen. And there we go. So concave up and concave down. So I always think of this is a cave, like the inner part here, that's the cave. So if the cave is pointing up, that's concave up. When the cave part is pointing down, that's called concave down. And a function can be concave up. The graph of a function can be, well, I guess the function can be concave up, or the function can be concave down. You can see it very simply in the graph. And it can be concave up or concave down. Concave up does not mean increasing. Concave down does not necessarily mean decreasing. It could be increasing or decreasing. Those two concepts are separate. Now, of course, a function is not all one or all the other. It could switch, because here it's concave up, and now here it's concave down, and here it's now concave up. Now, the point where it switches from concave up to concave down, and or concave down to that point where it switches is called a point of inflection. So the point where the concavity switches is called a point of inflection, and the textbook is going to show that explicitly. In the meantime, I'm just going to write it here. I'm just going to jot it down over here. The point at which the function goes from concave up to concave down, or vice versa, is called a point of inflection. So this point right here is a point of inflection because the curve is going from concave up to concave down. This point over there is a point of inflection because it's going from concave down to concave up. And we're going to see, so again, we are going to see how that relates to the second derivative. But let's just look a little bit more. Let's see, an epidemic has started, and you as a member of Congress must decide whether the current methods are effectively fighting the spread of the disease or whether more drastic measures or more money are needed. In the figure below, f of x is the number of people who have the disease at time x, and two different situations are shown in both A and B, the number of people with the disease, and the rate at which the new people are getting sick, which is f prime. So, I see. So f of now is the number of people with disease now, and f prime of now is the rate at which they're getting sick. The difference in the two situations is the concavity of f, and the difference in concavity might have a big effect on your decision. As you can see, a concave up function rises kind of like, I'm going to say faster. Now this is concave down. Even though this is rising, it's not rising as fast as that's rising. So if F is concave down, then the slopes are decreasing, like it's tailing off. And if it's so you could say like it's increasing at a decreasing rate. It's increasing, but it's increasing slower. That's the way to say it. And it appears that the current methods are starting to bring the epidemic under control because it's like the disease is tapering off. Whereas here, it looks like the disease is zooming up. So when it's concave up, the slopes are increasing, means the slopes of the tangents are increasing, and it looks like it's going to be okay. Notice that when it's concave down, the tangents are on top of the graph, and when it's concave up, the tangents are beneath the graph, below the graph. That's an important concept to remember. Okay, let's let's look at an official definition here. So y double prime, f double prime of x, or y of x. I don't need this. Or that's second derivative. If you want to write it with the Leibniz notation, you write d squared y dx squared, or d squared f dx squared. That's how you write it. Second derivative of f. Or you can write it. I personally like the this way. I find it easier. But either way, we'll use both all the time. So if f double prime is positive, if it's positive, then concave up. And if the second derivative is negative, then it's concave. Oh, this is a typo. Let me just. It is negative. This should be down. This is a typo. Let me fix that. So I'm gonna knock that out. See down. So positive is concave up, negative is concave down, second derivative. And this is the rule per se. Now I want to go. Now I just want to do is give you some examples of how to find these things and figure out concavity and so on and so forth. So let's just look at some examples. Now suppose we have the function y equals x to the third power. Well, y prime is equal to 3x squared, and y double prime is equal to 6x. Now, the 6x, well, sometimes 6x is positive, sometimes it's negative. The truth is, if I look at the number line, for all the negative numbers, 6x is negative. For all the positive numbers, 6x is positive. So that means the function is going to be concave down on the negative side of 0. And it's going to be concave up on the positive side of 0. Now, if you're familiar with this function, this is, and you should have learned this in algebra, I assume, the function actually looks like this. So if you notice, it's concave down over here, and you can see it's concave up over there. And let me just put that more in the picture, and we're good to go. Concave down, concave up. We are good. Let's look at another example, y equals x squared. Y equals x squared, y prime equals 2x, and y double prime equals 2. Well, 2 is always positive. That means that this function, meaning that no matter what the x value is, the function is always has a positive second derivative because 2 is a positive number. It's a constant positive number, and therefore this function is always going to be concave up for the entire x-axis. The entire domain of this function is going to be concave up, and that makes a lot of sense because we all know that the graph of this function, well, this is a parabola, and the graph is like that. And it's concave up the whole way. Let's look at a third example, y equals x. Y equals x, well, y prime equals 1, and y double prime equals 0. Well, y double prime is never, 0, y is 0. 0 is never positive or negative. 0 is neither. So that means this function is never concave up, nor is it ever concave down. And that makes sense because we all know that this is just this function here is a straight line. There is no concavity. There's no cave. So that makes a lot of sense. Okay, we're going to do some more fabulous examples. Here's a nice example. Y equals x cubed plus x squared minus 2x. So y prime is equal to 3x squared plus 2x minus 2, and y double prime is equal to 6x plus 2. And I want to know, when is this positive, when is it negative? So what I'm going to do is I'm going to set it equal to 0, and I'm going to solve for x. So I'm going to subtract 2 from each side. 6x equals negative 2. Of course, divide by 6. I get x equals negative 1/3. So negative 1/3, that's the cutoff point. That's the, let's graph this now. So if we draw a graph of this on a number line, so if x is negative 1/3, and we're looking at 6x plus 2, because that's y double prime. So when is this positive? So all I have to do is I just have to test one point on each side of negative 3. So I'm going to test negative 1, make that one of my test points. I'm going to test 0, make that another test point. So I'm going to put that into the function. I'm going to put that into x. 6 times negative 1 plus 2, that equals negative 6 plus 2, which equals negative 4, which of course is negative. So I'm going to put a big old negative here. And if I put 0 in, 6 times 0 plus 2, that's just 2, which is positive. That's what we need. I just need one test point. Since if one point is negative, this whole side is negative. If one point is positive, this whole side is positive, which means that the function is going to be concave down over here and concave up over here. And the actuality, actually have a picture of the graph that is, how do I do this? I'm going to switch cameras. And I'm going to share my screen. And here we go. This is, I typed this function into Desmos, and I got the red curve. Then after I did the calculus problem, I typed in x equals negative 3, and we see that point right there, that point right there is the point of inflection, or POI, as we say in the biz. Okay, let's do another exciting example. Okay, here's a nice little problem. So y equals x to the 4th plus 2x cubed minus x squared minus 2x. So we want to find points of inflection. We want to find the concavity and the points of inflection. So y prime is equal to 4x cubed plus 6x squared minus 2x minus 2, and y double prime, which is what we're going to need for the concavity and so forth, is equal to 12x squared plus 12x minus 2. And so I'm going to set it equal to 0. First, I'm going to divide both sides by 2. And make the numbers a little smaller. So we get 6x squared plus 12x minus 1 equals 0. Let's make that a big old 1 so you can see it's 1. And and now we're gonna that should be a 6. I'm sorry. I'm gonna redraw this whole thing. I just messed it up. This is going to be 6x squared plus 6x minus 1 equals 0. Now this is not factorable. I want to find the roots of this polynomial. I want to find when it equals 0. This is not factorable, so I'm going to use quadratic formula. So x equals -6 plus or minus the square root of 36 plus 24 over 12, which comes out to x equals -3 plus or minus rad 15 over 2. Now, if you would draw this graph, well, I can only draw it so well. I'm only that good of an artist. So let me just show you a picture of what this graph is going to look like. I actually have this. Let's switch. Now I need to switch cameras and get to my screen. There we go. Now I'm going to go here, share my screen. Okay, so here is the curve that we're just working with. Y equals x to the 4th plus 2x cubed minus x squared minus 2x. And it's this red sort of W looking sort of curve. Let me get my little picture out of the way. It's this red W looking kind of curve. And I just drew the line x equals -3 plus rad 15. That's that green line right there. And I drew -3 minus rad 15 over 6. That's the blue one. And you can see that it's concave up over here. It's concave down over here. And it's concave up over there. Now, let's go back. How do you know it's up, down, up? How do you know it's not down? How do you know anything? So let's go to let's go back to the other camera. And okay. So how do we know what regions? So what we do is these points where the second derivative equals 0, make them my this is -3 minus rad 15 over 2. This is -3 plus rad 15 over 2. Well, rad 15 is more than 3. So this is a positive number, and this obviously is a negative number. So I have 0 is in here. I'm just going to do -10, which is, these are pretty small numbers, but I'm going to do make this like -10. That's and I'll make this +10. So I'm going to test these 3 numbers. So 6 times -10 squared plus 6 times -10 minus 1 is 600 minus 60 minus 1, which is definitely definitely positive number. That's 539. And if I plug in 0, I get 6 times 0 squared plus 6 times 0 minus 1, which is -1, which is definitely a negative number. So it's negative here. And here, if I plug in 10, I get 6 times 10 squared plus 6 times 10 minus 1, which is 600 plus 60 minus 1, which is 659, which is definitely a nice positive number. So this is my POI. That's my POI. And this is concave up, concave down, concave up. And that's what we saw on the graph. I want to show you one more very important example, and it's coming up right now. Okay, now I have another quite important example. Very simple, but very, very important. Y is equal to x to the fourth. That's our graph, that's our function. So y prime is equal to 4x to the third. Y double prime is equal to 12 x squared. Now, if you notice, 12x squared, 12x squared is always positive. Because it's a square. A square is always, it's a positive number, positive 12 times the square. So it's which means y prime, i.e. y double prime is always positive. But when I do my thing of setting it equal to 0, which is how I found my when I set this equal to 0 and I solve, when I set this equal to 0, I get x equals 0. And so x equals 0 is a point that makes y prime 0. But since this is always positive, it's not a point of inflection. Just want to highlight this. So even though y double prime of 0 equals 0, whoops, 0 is not a POI because the second derivative does not change sign. So just because I have a 0 second derivative does not automatically mean I'm going to have a point of inflection. Now, as a matter of fact, if I graph this, y equals x, so we can get rid of all these. If I graph this, y equals x to the fourth, very simple function, very simple graph. I get something that's kind of like a parabola, but you see when x equals 0, that's not a point of inflection because it's concave up here, it's concave up everywhere. So it's not, you can see it's not a point of inflection. It doesn't change, doesn't, zoom in and out. So an inflection point, just to summarize, an inflection point is a point on the graph of a function where the concavity of the function changes, either from up to down or from down to up. So point B is a point of inflection because the curve is up here and it's down there. E is not. First of all, it doesn't change, so forget about E. But G is also a point of inflection because it goes from up to down. E is no good. Well, first of all, it goes from up to up, and whatever. E is not a point of inflection. Anyway, that's the a working definition. A working definition of concavity of point of inflection is that a point of inflection is a point on the graph where the second derivative changes sign, and because that's what's going to tell me that it's going from concave up to concave down. So the working definition is kind of similar to the definition. Well, everybody, it's been loads of fun, and bye now till the next time. Bye.